Let's see if we have it. Okay, so let's take a look at the syllabus just like we do every meeting. It is Wednesday, right in here. This is the 19th meeting, the 11th week. We have 17 weeks total, right? And let's see, Monday. Okay. This okay, we should do lab 4 today, single resistor. I postponed the due date of lab 3. Now lab 3 is due on Monday. Did you folks had any problem with lab 3, by the way? The resistor lab? Have you been having any problems with this lab? Okay, if you don't say anything, I'm going to assume that you haven't had any problem. But if you need help, I will be available for my office hours today. And what I want to do today, I want to start covering AC circuits, okay? And then we do lab 4, which is a circuit lab, a DC circuit lab. Remember, this is AC circuits, and by the way, if you know, I do not know if you noticed that, but I postponed homework 4 for a few days, for a couple of days. Let's take a look there at Wiley Plus. Homework 4, see to the 4th of May. I did that on purpose because this chapter involves material that we're going to start covering right now, okay? Is the AC circuit material. And open assignment, there are two questions on AC, 2 or 3 questions on AC circuit. Let's take a quick look. Alternating current. Okay, this one is on alternating current. This one is on alternating current. Let's see, 2. Let's see if we have more. Electric power. Yeah, it looks like it's only 2. That's right. Only 2 questions that are related to the material that we're going to start covering right now. The book included this material in chapter 20. I don't agree with that. I think that they should have included that in chapter 23. Because you need to know about the electric generator before you know about the AC circuit. Okay, and electric generator is covered only in chapter 22, right? They were covering chapter 20, what material that requires knowledge of chapter 22. Okay, so that I postponed homework 4 because some of the questions are AC circuits, are on AC circuits, a material that we're going to cover only now. AC circuits, a material that we are going to cover only now. In order to understand AC circuits, AC stands for alternate current, right? Alternate current, AC circuits. You must understand the generator, which is how AC current is generated. You need, right? You need a generator to produce alternate current. The alternate current is that, oh, I'm not sharing the screen, right?
No.
Yeah, okay. Don't forget to tell me that. Hiccup. Let's repeat what I did, right? Here you go. We are writing here on Wednesday, 22nd. I'm going to start chapter 23. And later on, you're going to do lab 4. Chapter 23 is AC circuit. The third exam is scheduled for for the Wednesday before the holiday, the Memorial Day. So it's going to be how many weeks? 1, 2, 3, 4. 4 weeks. 4 weeks from now is going to be exam 3. Okay. And like I mentioned before, let's go back to our notes. One more thing, right? I have to tell you. There is a course evaluation, by the way. Okay, the course evaluation opened up. You have the opportunity to evaluate the course. Let's go there in Canvas. Let's see. Okay, course evaluation. Okay, you have until April 26th, which is a Sunday, to evaluate the course. You go on modules, and at the top, right in here, okay, you can open and provide your sincere opinion about the course. And you have until Sunday to do that. Okay? Go, and that's completely secret, right? Private. Whatever you say there, your name is not going to appear there. Okay, course evaluation and course evaluation. You have until Sunday to evaluate this course on Canvas. I postponed homework 4 because some of the questions are on AC circuit, a material that we are going to cover only now. Let's see here, and I want to go back in that chapter chapter 20, that's 22. Right in here. Okay, electric circuits are here. Okay, so note that they covered the electric circuit before they covered the generator. So we will be covering this material right now. It's a very fun material to cover, especially if you get to understand it. It's much easier to understand direct currents. Okay, it's much easier to understand direct current, DC. Alternate current is a little bit more difficult. But once you understand, once you have a grasp, it's really fun to play with it. It is the type of current that is transmitted to our houses in the power lines that we see out there. The power lines that we see out there, okay? But don't forget To understand alternate current circuits, you must understand the generator, which is how AC current is generated, is produced. Okay, it's produced, it's better. You need a generator to produce alternate current. And alternate current is current, alternate AC current is a current that is generated by rotating a coil in a magnetic field, right? In a uniform magnetic field, in a uniform magnetic field with constant angular velocity. Remember, angular velocity is not linear velocity. Rotate with constant angular velocity. Because of the constant angular velocity, and it is because of the constant angular velocity that the voltage generated by the generator varies sinusoidally. Okay, so here we go. Sinusoidally with time. AC circuit. Sinusoidally with time. And be reminded, right? That is, there are two circuits, right? The DC current, two circuits, DC circuits, current flows in a single direction. Current is constant and flows in a single direction. Power source is the battery. AC circuit, current flows in both directions. Power source is the generator. Use the electric induction phenomenon, which is the electric induction phenomenon. We can say that the AC circuit is the electrical counterpart of the harmonic oscillator, mechanical harmonic oscillator. Harmonic oscillator, okay? Harmonic oscillator moves back and forth, right? The current in an AC circuit also moves back and forth in the circuit. And here is a table comparing those two circuits. DC circuit, AC circuit, direction of the current one direction, either clockwise or counterclockwise. AC circuit, the current flows in both directions. Is in at a given instant of time is flowing in one direction, it stops, becomes momentarily zero, the current, and then starts flowing in the other direction. Momentarily stop and flow in the other direction. Boom. Bouncing back and forth, bouncing back and forth. That's what AC circuit is all about. We have some nice simulations. Let's see if I can get that for you, that illustrate those two different circuits. And with those two different circuits, we can even play with those two different circuits to better understand how it works. What's going on here? I'm trying. Let's see here. I'm trying to get a computer program here to show up in my computer, but it's not running for some reason. VPN. VPN. Let's see. That's the one I'm trying to open. I need to close it. No, that's not the one. My VPN interfered with my Google search for some reason. But let's try it here. FAT, Colorado. Yeah, simulations, FAT simulations. FAT simulations. We don't want Portuguese, we want English. Let's get English here. Okay, good. Physics. It has some simulations here that allows you to visualize how current flows in a circuit. Physics, motion, sound, electricity. That's what we want here. Electricity, magnets, and we can even put together some virtual circuits. Okay. And right, let's see, construction kit. Yeah, this one. Let's see if this one has DC and AC circuits, right? Check this one. I'm gonna put it, check for to better understand circuits, better understand circuits. Check the FAT website. In case you cannot play with the actual circuit, play with a simulation of the circuit. Play with a simulation of the circuit. This one here, for instance, there are others that you can look at that too. This one is AC, right? This one is AC. Yeah, and we also have DC. Okay, and here you go. Let's play it. Let's see if we can do something with this one. AC voltage. That's what we're doing here. Okay, so you can go ahead and put together your circuit. Here you go. Wire, one wire here, right? You're going to connect the element of the circuit. Here you go, the resistor. You always need a resistor in your circuit. Another wire, and I'm going to put a switch, the same switch that you have in your wall to turn on and off the light. We use here in those circuits. Here you go. Let's see if we have battery. Yeah, this one is AC, so they don't have battery. They have just the generator, the AC voltage generator. Okay, here you go. Wire. Look at the electrons. Do you see the electrons in bluish color? Those are the electrons right in here. And I'm going to put my AC generator. Right here. Okay. And now when I close the switch, okay, oh, look what happens to the electrons. They're going to move back and forth. Electric current is the motion of electrons, right? And this circuit has a given frequency as well. And not only has a given frequency, but they also have a given amplitude that can be varied. Let's see if I can change I can change the frequency and I can change the amplitude of the circuit. The amplitude of the circuits is dictated by the voltage, the peak voltage. Right now we have a 9-volt peak voltage. If I increase the voltage, okay, go ahead and access this website, play a little bit with it. You might want to start with the DC circuits because the C circuits are simpler than AC circuits. Okay, click again the generator. I'm going to increase the peak voltage again. By increasing the peak voltage, electrons travel further, right? I'm not changing the frequency yet. I increase even further. Yeah, here you go. We don't see that in a AC circuit, but that's exactly what it looks like in the microscopic realm. Exactly how the electrons behave in the microscopic realm. And then I can change the frequency too, right? I can slow down a quarter of a hertz, a tenth of a hertz, right? Whoa, see? Because of the frequency is so low, the electrons can travel further, right? Whoa. But if we increase the frequency, they're not gonna travel as far. Let's increase the frequency. Yeah, see? Oscillates almost in a very small distance. Here you go, 2 hertz. There are devices out there that allow us to create those circuits and to change the frequency of the circuit. There are devices out there that allow us to do that. Not only there are devices that allow us to do that, to change the frequency, but there are devices that allow us to measure the frequency as well. The frequency and the amplitude of the circuit. Let's see, voltage chart. Okay. Here you go. I'm going to connect at the ends here of the resistor. And you're going to see, okay, yeah. Do you see that? Data is out of range, right? Because the amplitude is too high. And this is an oscilloscope. My oscilloscope cannot handle high amplitudes here. So we have to decrease the amplitude of the circuit. Let's see, it's 120 volts. See here, it can go only up to 10 volts. So let's bring it down. So we will be able to see the sinusoidal. Here you go, 8 volts is enough. Here you go, sinusoidal behavior. Okay. If I increase the frequency, here you go. Now you start to see the sinusoidal variation of the voltage in this AC circuit. So I suggest you play. Let's see how we're gonna do that. I'm going to send that through WhatsApp, no, chat. Chat. Okay. Check this AC circuit simulator in FAT. I think it's like that. That's just one of the simulations that you have. You might want to look at others one as well to understand circuits. Let's go here. This is that is the DC circuit as well. Let's see this one here. This is not DC, this is AC. This one here is AC as well. This is AC as well. Okay, this is AC. Let's go back. PHET, right? And the simulations educated, okay. Capacitor circuits, AC. Okay, this one is DC. Seems to be DC. With a capacitor. But let's go back to that other page we saw. Yeah, okay. Here you go. Here's the generator, right? That's a simulation of the generator, similar to that one that you saw for Fender, right? Fender. And magnets and electromagnets, magnet and compass, Faraday's electromagnetic lab. That's the electromagnetic, what we just covered, right? Electromagnetic what? Induction, electromagnetic induction. Here's for AC circuits, that's for AC circuits as well. Let's see, I want to see that. Okay, that's the DC kit. You want to see that as well. Let me get that. Here you go, Pat. Chat. This simulation is for DC circuits. For DC circuits. Here you go. Those are very helpful to visualize. And like I said before, let's go back to the DC. You're going to see just like the AC circuit, we can build circuits from scratch. And that's what we're going to do in the lab today, okay? So it's very convenient that I am okay, doing some noises here. That you got battery, see? Battery or power supply. Power supply does the same thing as the battery does. Oh, oh man, that's so annoying, this noise. I'm gonna put my switch here. That's a simple circuit. What the circuit that we are going to do today in the lab is exactly this circuit here. Power supply, a switch, and a resistor. Here you go. Power supply is the battery. Okay, I'm gonna close the circuit. Here you go. Do you see the electrons moving in only one direction? In this case, it's counterclockwise. That's the type of lab we're going to do today, lab number 4. And if I increase the voltage of this battery, right now it's 9 volts. What's going to happen to the electrons? They're going to move faster. The current increases. What does it mean the current increases? When the current increases, the electrons move faster. The electrons move faster, okay? So you can play with that. And then we have the voltmeter here. The same device that I've been talking to you, right? You can measure the voltage across the resistor, which is going to coincide with the voltage of the battery. I think it's my air conditioning. Here it goes. It's 91 there, right? It's going to be 91 here as well. Okay? Because I have just a single resistor, right? If I put a second resistor there, then the voltage is going to be split between the two resistors. Now let's slow down those electrons. Okay. I cannot, I can switch the polarity of the battery, see that? And now the electron is gonna flow in the other direction. One direction, the other direction. Depending on the polarity of the battery, the electrons flow in different directions. Okay, and when I change the polarity of the battery, the polarity of the resistor doesn't, it does change, yeah. The polarity of the resistor does change. Okay, negative. Okay, now it's positive. 14 volts. Okay. So those are the two simulations that I want you to play with to understand better the course, to understand better the material. And now let's go back to the lecture, right? That is, here you go, that's the DC circuit. Okay, simulation for AC circuits. Simulation for DC circuits. Remember the word of the current, this AC versus DC, right? DC, word of the currents, I'll say DC versus AC and AC1. AC1. But AC won the battle to electrify the houses, right? Won the battle to electrify the houses. DC won the battle to electrify the devices. The devices that we have out there, including your cell phone, they're basically DC circuits. Going back here. Types of AC circuit. Okay. There are different types of AC circuits. The simplest one is the AC circuit with a resistor only. The easiest one to understand as well. Then you have AC circuits with a capacitor only. We have AC circuits with an inductor only. And then we have a combination of the above elements. Resistor and capacitor, resistor and inductor, capacitor and inductor, and then we have the combination RCL. Can combine all those three elements in a single circuit, and the circuit behaves in a different way. Okay? Let's start with the AC circuit with the resistor. AC circuit with the resistor is the one that was covered in chapter 20, section 20.5, which we are going to cover now, only now. AC circuit with a resistor only. And I want you also to follow closely on the book. Let's take a look at the book. Here you go, course resources. Launch. Here you go. Okay, alternating current. Here you go. That's the symbol of the generator, right? With a wiggle inside it, a sinusoidal symbol, and the resistor. That's what we have there in the power plant. The power plant that generates the electricity. Here you go, AC generator. Here's the power plant. and the AC generator is connected to your house, several houses, not just one house, but several houses. And that's the notation that they use. We're going to use this notation as well. Okay, and the voltage that varies in a circuit with a resistor only is a sinusoidal voltage. V0 is the peak voltage. We usually write that down as being 2 pi f. F is the frequency. And 2 pi f, we have a name. We call it an omega, angular frequency. Okay. F is the regular frequency. Regular frequency, comma, omega is the angular frequency, which is 2 pi f. 2 pi f. Symbol. Here you go. The angular frequency. F. Like that. Okay, so the voltage that we get at home is 110 volts. And 110 volts is this term right in here. The frequency that we get at home is 60 hertz and varies from country to country. Okay, let's take a look at the internet. Okay. Oh gosh, I can't. What a shame. Gotta figure out how to turn off my VPN. For some reason, my VPN interferes with my, and I cannot even get it here. That's okay. Okay, let's go. AC circuits in different countries. The standard, right? Mains electricity by country. Let's see. Let's take a look. That's Wikipedia. Here's the overview, right? That's Wikipedia, voltage and frequency. What mains electricity vary in voltage and AC frequency across the world, okay? As shown in the adjacent map and the table below, premises in most of the countries receive a supply of between 220 and 240 volts nominal at the AC frequency of 50 hertz. North America is the biggest exception. Most countries, are powered by 220 and 240 volts peak voltage at 50 hertz. North America is the biggest exception. Brazil here, okay, I'm originally from Brazil, has both 220 and 110, and also frequency of 60 hertz. So let's see here. With the notable exception of North America, premises around the world receive either a three-phase supply or single-phase supply. You don't have to worry about this three-phase or one-phase, but a choice of either 120 or 240 volts at 60 hertz, okay? Each circuit in the premises can be connected to either 120 or 240 volt supply, the later being used for appliances with larger power requirements. But there are also 380 volts standards out there, okay? Plugs, we have different plugs from country to country, from regions to regions, right? Here you go. That's a plug here used in the States. No, wait a minute. Type A. It doesn't say. No, it's not United States. It's round. It doesn't look like round to me, the picture. This one is in the States. That's in Europe. This is round, but this one looks like the one in the State. Okay. Belgium, every country has a slightly different plugs. Okay. Table of main voltages. Afghanistan, 50 hertz. American Samoa, right? 60 hertz, 120. Anguilla is 110. Antigua, right? Aruba, 127 is slightly different. Bahamas, 120. Barbados, 150. Depending on the country, they use different standards. If we go, let's see, Brazil is 110. Oh, we don't have Brazil here. Let's take a look. Brazil, right here. 127 to 120. And it's 60 hertz, just like in America, in North America. Botswana, that's Africa, 50 hertz. Let's take a look at US. United Canada, right? Canada is North America, 120, 60 hertz. Should be similar to the United States. That does not mean that you cannot generate other voltages with your generator. You can, you can, okay? It just happened that different countries chose different standards for some reason. Here you go, 120, 240, 120, 208, 277. So we have 3 standards in the US, 60 hertz, okay? So that's where it goes, that 120 goes right in here. The frequency here should be 60. The value of the frequency of the current. Got the idea? So you have your generator rotating at 60 times per second, okay? You have your coil, right, of the generator rotating at 60 times per second. So let's look at the mass behind that. I already wrote that up in here, but I'm writing it again. Angular frequency. Frequency is the frequency of the circuit, number of oscillations per unit of time. Omega is the angular frequency. The unit is radians per unit of time. And here you go. You do know, here you go, I like to put V as being a function of time. Okay. And let me see, we usually, when we are dealing with AC circuit, we usually represented by lowercase v, but not in this book. Okay, so let's stick to the notation of the book. We usually, when we're dealing with the AC circuits, the notation becomes a lowercase v, lowercase I, okay? But let's keep on using the notation of the book so you don't get lost, right? So here you go, it's a function of time, right? And Ohm's law also works. Ohm's law also works for AC circuits. So when you have V of t and you have a resistor in the circuit, this V of t is going to be equal to the resistance times the current, which will end up being a function of time as well, right? Here you go. You want to use a capital I. Like that. Okay? And now that we have applied Ohm's law to our AC circuit, we can obtain the relationship for the frequency in terms of the peak voltage the resistor and the frequency of the circuit. This resistor goes away. Okay? And that, oh, and by the way, V naught over R is exactly the peak current. Can be written down as the peak current. Like that. I not. And now, let's put the voltage equation and the current equation one next to each other. Like that, right? Notice that they both multiply it by sign, right? And whatever is inside the parentheses of the sign is exactly the same term. When you have a situation like that, okay, when we have the above two relations, comma, we say that both the voltage and the current are in phase with each other. Okay? They are in phase. And the current are in phase with each other. We can even illustrate that with a graph, right? If you plot this graph, those two graphs are going to start exactly in the same place. Let's take a look here at here you go. I'm gonna plot. Here you go. Here's the graph of the voltage, right? If I plot the graph of the current of an AC circuit, the value of the current is going to start exactly in the same spot. Let's see how I'm going to do that. Here you go. Instead, okay, let's use this one here. Instead of 110, let me use 90. Let's use 90. It is not T, sorry, it's going to be amperes. By the way, 90 amperes is a lot. But, oh, what happened here? Ah, that's why. Supposed to be the other. Here you go. And then when I plot this other graph, they're going to be in phase. They're going to, what does it mean they're in phase? The zero amplitude, the zero, not only zero amplitude, but the zero voltage and the zero current coincides in the same graph, right? So I'm going to add, here you go, select data, add current, X value is all of that, just like we did in the labs, right? And then I'm going to do that for the Y values. Everything here. I'm going to go to 68. And then we are going to have, oh, what happened? What a shame. Oh, here you go. We got it. This one, the blue is the voltage. The orange is the current, right? So you can see that they are in phase. They cross the zero axis at the same spot. You can have currents that are going to be slightly shifted, by the way. You can have. Depending on the device that you put in the circuit, you are going to have currents that are off phase. Okay, let's see. I want to copy that into your notes. Snipping tool. Get this one here. Right here. AC voltage in blue, AC current in orange. For an AC circuit with a resistor only, both voltages and current are in phase. Okay, are in phase. How that we draw a schematic, a circuit schematic. The circuit schematic is drawn like that. If you're going to work with electric circuits, you're going to see this thing all the time. And most likely you will have to work with those things. Okay, the current is flowing back and forth, right? Just like in that simulation that you saw. Bouncing back and forth, right? Going back, right? Going back to the, okay, this one is DC. Well, I didn't save the AC. I didn't save the AC, right? But that's how we should represent it. At a given moment in time, the polarity of the alternate is going to be positive to the right side, negative to the left side. And let's get my drawings as well. My illustrations. AC circuit right in here. Okay, so 3 different types of circuit. Circuit with a resistor, circuit with a capacitor, circuit with an inductor. Okay. And we are concentrating on this one here right now. And using Kirchhoff law. Now you can apply Kirchhoff loop law for this circuit as well. Okay, and how do you do it? Another way, right, of deriving that equation that you saw in there. And you're going to use, we are going to need to use Kirchhoff's Loop's law. What's going on here? Okay. Okay, this is a simulation that I have. Let me show you this simulation here for you. So you understand, here you go. Here you go, here is my AC circuit, right? It starts with a negative polarity on the left, a positive polarity at the right. The resistor is gonna have a positive polarity at the right and a negative polarity on the other side. The positive of the resistor faces the positive of the generator, right? As time goes by, what happens? Voltage increase between the terminals of your generator. So what does it mean? It means that we have a buildup of electric charges. See now, before we had only one charge on each side, right? And now we're gonna have 2. A little bit later on, you should have 3. And then, and then it reached the peak, let's say. That's the highest voltage that the generator achieves. And now it's going to decrease the voltage, right? And eventually it will become neutral, no charges at the leads, and the current is going to invert direction. See that? That's exactly how you should visualize those circuits. This is a oscillating circuit, right? This is an oscillating circuit. A circuit that oscillates as time goes by. That's the picture that you must have. How do we use, again, how do we use Kirchhoff's law? Well, we already did something like that in a different way, but I want to do it again using Kirchhoff's law, because we're going to be using it again. Here we go. We start at this point here of the circuit. We cross the generator, right? When we cross the generator, we write V sub G. We move towards the next element. We are going to cross the resistor. We lose electric potential. We lose electric potential energy because the resistor is consuming the energy, the potential energy. So we put a negative here, VR. The VG is positive because we're going from the negative polarity to the positive polarity. And then we can go back to the initial point. We write down equal to 0. Okay? That's exactly how Kirchhoff's law works for DC circuits as well. But the VG of the generator, you already know, is going to be given by, here you go, I'm going to write it down. VG of the generator is equal to this term, VG of the resistor is equal to this term, Ohm's law. And then we replace in our equation, we get something like that, just like we got before, but now using Kirchhoff loop law. And then you can write down the current in terms of the voltage and the resistor. There is another way of displaying those equations, and that would be the phasor diagram. It's a very nice, it's a graphical way of illustrating what you see here in the equation. There is a graphical illustration of this equation. There is a graphical illustration of the above equation called the phasor diagram. It's a very intuitive one. Let's take a look at the book. I want to take a look at the book, make sure that it covered as well the phasor diagram. Let's see. Okay, it's not here, the phasor diagram. Let's see if it's in here. Oh yeah, it does have the phasor diagram here. Okay, yeah. That's a phasor diagram. You wanted to see, not this illustration here, right? But those vectors that you see in there. And I'm going to represent, there is a graphical illustration of the above equation called the phasor diagram. For the voltage, we represent the voltage V in the following way, okay? We represent it as a vector of length V naught, peak voltage, right? Your 110 volts, for instance. And whatever is projected along the y-axis is the voltage as it changed with time. And this vector that you see right here, it rotates in this diagram, X and Y. It rotates with a, as time goes by, this vector rotates and this projection either increase or decrease, right? See the vector rotate at omega t, right? Keep in mind this phasor diagram is very useful for the voltage of the generator. Here you go. Phasor diagram for the voltage of the generator. And we get the same phasor diagram for, here you go. So this illustration here, it represents exactly this equation, okay? Represents exactly this equation. As 2 pi f t increases, this vector keep on rotating, right? And V naught sine 2 pi f t is going to be this projection that coincides with the V as a function of t. And what about the current? The current for a circuit with resistor only is going to be in phase with the phasor diagram of the voltage, right? You go, here's the same angle at time t equal to whatever. Same angles here. And those two phasors are going to rotate with the same angular velocity. Combine them in the same diagram, just like we have in the book. It's a very simple idea that ends up being very powerful, by the way. Solve problems. You combine them in the same diagram, you have the voltage below and the current above, right? And they are sticking to each other, coinciding with each other, rotating in the same angular velocity. Now we are going to do the capacitor, right? Here you go. The same, what you see here is the same as I have it there. And is this circuit right in here. Now replace the resistor with the capacitor of capacitance C. And let's see what's gonna happen. Replace the resistor with the capacitor, with capacitance C. We'll use the Kirchhoff loop law to find an equation for this new AC circuit and write the charge Q and the current I. It's an example that I want you to do. And I want here you go. That's the circuit right in here. The diagram. Oh, we're almost at the point where we should break, right? Take a break. And let's apply Kirchhoff loop law. Okay, so when the generator is in this configuration, right, we must have positive charges here in the capacitor and negative charges on this other side. Okay, and I want to do the Kirchhoff loop law for you before we go for our break. Just like before, we start right here at this point, we cross the generator. We have the first term that's going to be VG. Then we move along the circuit, cross the capacitor. We're going from a position of positive charges to negative charges. What does it mean? It means that they are going to a point of higher potential to a point of lower potential. And when we do that, we must have a negative sign here for the voltage across the capacitor. VG is just like before, is the V naught sine 2 pi f t. And VC comes from the equation, from the definition of capacitance. Okay, definition of capacitance. And we invert VC, Q over C, we get this equation right in here. Right in here. V naught sine 2 pi ft minus Q over C equal to 0. Okay. And the charge is going to be in phase with the voltage. Notice that it is the charge that's in phase with the voltage for the capacitor. However, the same cannot be said of the current. The current is not. Same cannot be said of the current, okay? Remember that the current is delta Q over delta T, right? It's delta Q over delta T. I'm gonna do that here. And because you have delta Q over delta T, the current is going to be out of phase with respect to the voltage. In order to prove that mathematically, we have to do differential calculus, okay? But I'm not going to do, of course, I'm not going to ask you to do differential calculus here, but I'm going to ask you to memorize the final result. When you take the delta of this function with respect to t, the sign switches to cosine. On the top of that, the 2 pi f goes outside the term, okay? And now you can see that the current, whereas the voltage has a sine, the current has a cosine. They are phased out by 90 degrees. The cosine of 2 pi ft can be written down as sine 2 pi ft plus pi over 2. So we say that the current is out of phase with respect to the voltage by a 90-degree angle. We say that the current leads the voltage. And that's the result that you gotta memorize. Okay, I'm not doing the derivation here, but they step from here. If you took calculus, you know how to do that, right? But you're not required to know calculus here in this course. That's why you have to memorize that relation. This term that you see right in here, the amplitude term of the sine, is the current, is the amplitude of the current. Here you go. One more student coming in. Let's see, Jeranis. Okay, and I'm not. Let me just. The charge is in phase, but not is in phase with the voltage, but not the current in a circuit that has a capacitor combined with a generator. We don't need this one, right? The charge is in phase, but not the current. Here's I not means, and let's see what time is that. Let's go another 4 minutes. 10:51. Yeah, let's go another 4 minutes before we go for our break. Okay, how do we draw that in a phasor diagram? Phasor diagram. We start with the voltage. We show the charge. Q naught is the maximum charge that goes in the capacitor, which is in phase with the voltage. Yeah, and now the current. The current leads the voltage. And we're going to put everything in a single phasor diagram. I'm putting them separately, right? Here you go. Here's the current. Omega t plus 90 degrees. And this guy is, you gotta visualize it rotating. Okay, rotating in real time. And here is the final phase diagram combining everything: voltage, charge, current. So it's a capacitor in an AC circuit. The current leads the voltage by 90 degrees, or the voltage lags the current by 90 degrees. Either way, it all depends on your point of reference, right? What else? What else can we talk about it? There is one more important idea. Let's see if you have time. Recall from Ohm's law, right? V naught is R, I naught. V naught is R, I naught. And I want to go back right in here. See I naught right in here? R, I naught. And here you go. V equal Ri, right? I'm gonna play a little bit with this relation that you see right in here. Recall Ohm's law. V I naught is equal to V naught over R. And we do have a same relation for the circuit in the capacitor, right? See, the V naught that we have here correspond to this V naught. But the R that goes downstairs correspond to the inverse of this term. Okay, that this I naught is the I naught that comes out from the current with the capacitor in the AC circuit. Okay, and I can make a relationship between this term that you see here with the resistance in the Ohm's law. Okay, and we can call this, here you go, I'm gonna write that in a different way. It's better if I write like that. Okay, he called that that's the current in the AC circuit is the capacitor. I'm going to here write this term, this 2 pi fc term here in a different way. Okay. What you have right in here is exactly what you have right in here. Okay. And now you have the V naught that corresponds to this V naught. And you have this term here that has exactly the same unit of a resistor. We do not call it a resistor, this term, because it's not a resistance, but it's something similar to a resistance. Okay, it has the same unit of a resistance, but it's not a resistance because it involves the capacitance and the frequency. So we give it a different name. Okay, the unit is the same as the unit of the resistance, is the ohm, but we give it a different name because it's not exactly a resistance. And because we give it a different name, we also give it a different symbol. Okay, it's a X sub C. And what name do we give to it? The above new term, we give a name we give the following name, the capacitive reactance, or the AC resistance. Don't say AC. Capacitive reactance. Don't say the AC resistance, right? Capacitive reactance. Okay, so remember that. And now the next example is going to be an example with the inductance. Let's take a look where we are right in here. Here you go, the current making a 90-degree angle, leading by 90 degrees with respect to the voltage. Inductors and inductive reactance. Let's see, what is the capacitive reactance? Okay. See, here is the current, right? When we plot how the current varies with respect to time and how the voltage varies with respect to time, the current is ahead of the voltage. Okay? This point here in the voltage is behind this point here in the current. In the phasor diagram. Let's see, and does you write down where is the term for the capacitive reactance? It's not showing us. One more minute to go so we can have our break. Yeah, for some reason it doesn't show the capacitive reactance here in the book, but that's what it is. Then we are going to do the same for the inductor, okay? We're going to repeat that for the inductor, and we are going to see that the current of the inductor is going to lag the voltage by 90 degrees as well. It's not difficult to memorize. Not difficult to memorize that. So 10:59. Any questions about that before we proceed? Of that we call this term the capacitive reactance. Okay, break 11 a.m. to 11:15 a.m. When we return, we're going to do lab 4. Let's see if we have any questions. No questions so far. So I'll stop sharing and I see you in 15 minutes. Record setting. I am back here. Let's share the screen. And that is the material for the resistance in an AC circuit and the capacitor in an AC circuit. The next one they're going to do is the inductor in the AC circuit, but we are going to do that on Monday because now we're going to do the lab number 4. Let's take a look here, lab number 4. Lab number 4, the simulation is already here for you. Why don't you access this link? Go ahead, access this link and play a little bit with the simulator. You know, notice that as let's see if I can get this thing here. Oh yeah, notice that we can increase, right, the voltage and decrease the voltage of the power supply, the battery, right? When we increase the voltage of the battery, the current increases. What does it mean, the current increases? It means that the electric charges are moving faster and faster. And those are the negative electric charges that are moving in the circuit. Okay, that's the type of lab that this one today is. And in this lab, what are you going to do? We are going to change the resistance of the resistor. Okay, I can increase the resistance and decrease the resistance. When we increase and decrease the resistance, will the current increase or decrease, right? Notice the bands here of the resistor. The bands are changing color, right? What was exactly what we covered last lab. The color code of the bands in the resistor. Let me turn off the electron. I don't want that. Oh, yeah, here you go. When I change the resistor, the color band, the, the colors of the bands, they change. This is 119 ohms. This 1, 2, 3, 4. The next one is going to be 113 and so on. Okay. That was exactly that we covered before. And notice that when I decrease the resistance to 2 ohms, the circuit burns out, right? 4 ohms. At 4 ohms, the current is so intense that the circuit catches fire. The circuit catch fire, okay? And the battery too. Here is 0 ohms. Now is the battery that caught fire. 0, 1 means that we are short circuiting one polarity of the battery to the other polarity. Never do that to a battery of yours. And let me get I need to get to the spreadsheets for lab 4. Someone is trying to come in. Lab raw data, lab number 4. Okay. Let's see. We have and 11. One more student coming. Well, $16. Stop share. You don't need to see that, right? And 16. In this meantime, go ahead, start playing with the simulation there. Let me send you the link for the simulation again in case you missed the link for the simulation. Here you go. For DC circuit, this link is going to be useful for the lab. 17, 18. Now I can share the screen with you again. Let's see, I gotta go. Mhm. Physics 7. And now I am going to upload the spreadsheets to your group folder. Group 1, Group 2, Group 3, Group 4, Group 5, Group 6, Group 7, Group 8, Group 9, Group 10, Group 11, Group 12, Group 13, Group 14, Group 15, Group 16, Group 17, Group 18, Group 19. Okay, so everybody should have their spreadsheet now. And I'm gonna get my notes for lab 4. Okay. Okay, so here goes. Lab number 4. So just as a reminder, insert, let's get that. Okay. So lab 1 and 2, we map the equipotential lines for two different electrode configurations, parallel plate, and the other is the concentric cylinders. Lab 3, we measure the resistance of different resistors and compare these measurements with the color code or the nominal value that's in the table. Okay, that's what we did in lab 3. We plotted the resistance values obtained with the multimeter against the resistance value obtained with the color code. That's what we did, the nominal value. And during these experiments, I introduced you to different equipment and devices, right? Right in here, we use the voltmeter. The voltmeter option of the DMM. Right in here, we use the ohmmeter option of the DMM. Ohmmeter means measure the resistance. During this experiment, I introduced you to different equipment and devices, right? In this in this new lab, we will use the ammeter option, ammeter option of the DMM to measure current. So you can measure volts. Here you go, of the DMM to measure volts, right? Voltmeter measure volts, ohmmeter measure to resistance, and the ammeter measures current. So you can measure all those three important quantities in electricity. And so today we will continue with this introduction by putting together the simplest circuit you will ever find in your life. A circuit with a single resistor. And the circuit with the single resistor is exactly that one that we saw in the FAT simulation, right? This one right here. I'm gonna pull it apart. I'm gonna pull it apart and put it together all over again in case that you missed what I did initially. You already have the link for this simulation, right? I'm going to clear up my, how do I clear that up? Interesting. Let's put it back. I'm going to start from scratch. Yeah, let's start from scratch. Here you go. Circuit construction kit, DC. You already have the link for that. Okay, introduction. That's what we do in an actual lab. You know, we use actual wires. We use actual power sources. We use actual resistors, right? Here you have an idea of what we do in an actual lab with this simulation. So here you go. The circuit that we build. Let me get my illustrations as well. Lab slides. Single resistor. Right in here. Okay, here is the digital multimeter that we use there at LA Harbor. It's exactly like that. It's a a smaller device like this one, has a bluish color. Okay, I prefer to show that to my students because that's exactly the device that we use at LA Harbor. And the circuit that we are going to put together that's the schematic of the circuit. You already have seen something like that in your problems of circuits. You already seen, right? Something like that in the circuit problem that you're solving in the previous chapter. Yeah, so I want to add a thicker. Here you go. Like that, yeah. The battery, this represents the battery. This is a wire, and this is the resistor. And that's what I'm going to reproduce in that simulation. I'm going to reproduce exactly what you see right in here in the simulation. You go, the wire, right? The battery. The wire connect to the battery. The other wire connect, the other lead of the wire connect to the battery. We are going to close this. I'm going to put a switch. I didn't put a switch in that one. Okay, let me show you how a switch looks like in the right in here. Let's see, I'm going to like that. That's how we draw a switch, okay? This thing can go close and open, close and open. If you open, no current flows through the circuit. If we close, the current flows through the circuit. And it's exactly how I'm going to depict right in here. Let me cut that and put there at the top. It's not difficult to play with this simulation, okay? I just don't like this noise that he makes. I think it's annoying. Right in here, get another wire. I gotta put resistor here at the bottom, right? That's the resistor. Here you go. Another wire. Oh. And a final wire. Here you go. That's how the circuit looks like. The bluish circles are the electrons, which has negative charges, right? That's the circuit that we put together. What do we do? Go ahead, open your spreadsheet. I'm gonna open one of the spreadsheets as well. Lab report. Of data. Here you go. And here, what we're going to do here in this lab, we have a table here. The first table, several tables, more than one table, okay? Make sure you put your group number, put the student names here, right? And what do you do in this lab? In this lab, we start with a power supply right in here. See V supply, V sup stands for supply, power supply. The units, here's the row of units. The units of voltage is volts. Already filled that up for you. And what we're going to do, we're going to vary. We're going to get this circuit that we saw right in here. Let me turn off the electrons. And we're going to vary the voltage supplied to the circuit. We're going to vary this voltage here, okay? In the simulation, I can vary the voltage as well. I can start from 0, can go all the way up to 10. Oh, actually, I can go all the way up to 120. But in our lab, in the spreadsheet, we are not going to exceed 10 volts. And that's exactly what you see here. We start at 10 volts, 8 volts, 6 volts, 4 volts, and then go to 2.8. And then what else we're going to do? We invert the polarity of the battery in the circuit, okay, to produce negative voltage. See, that's exactly what I did here. I inverted. The battery was like that before. This was the north. This is not the north pole. This is the positive, and that's the negative side of the battery. I invert the polarity. When I invert the polarity, I will be providing negative voltage. Okay, I will provide with negative voltage. And what we want to do, we want to verify Ohm's law by doing this experiment. Once we vary the voltage, we are keeping the resistance constant. We're not going to change the resistance whatsoever. And then we measure the voltage across the resistor, and we measure the current that flows through the circuit at 2 different points in the circuit. Okay, the current at 2 different points should be almost the same. Okay? And we do get almost the same, a very small difference only. Let's see, 3 in 500. The difference that we get in this spreadsheet, the specific spreadsheet, is a difference of 3 units in 500 units. Is a very less than 1%. Less than 1% difference, okay? So let's see, I want to go through the roster one by one. Make sure you are ready to do this lab. Today is the 22nd. Oni, are you there? Hello, Ani.
Yes, I'm here. Yes, I'm here.
Do you have your spreadsheet there open?
For lab 3 or
Four.
lab 4?
Lab 4.
Yes.
Okay, download it and open. Okay, now Mirage is not here, right? Susan Acosta, are you there?
Yes, I'm here.
Okay, did you download your spreadsheet?
Yes, I have.
You opened it as well?
Yes.
Okay, thank you. Evelyn, is Evelyn there? I don't see Evelyn. Next is Christina Graciela. I don't see Christina. Next one is Queen Castaneda. I cannot hear you, Queen. It looks like you're trying to speak, but I cannot hear you, right? If you can, you may type there in the chat window. Okay. Just want to know if you downloaded the spreadsheet and if you're able to open it to follow the whole procedure. Okay. Emily Serna. Okay, thank you. Is Emily there? I don't see Emily. Next is Isabella Cisneros. Oh, Emily. Now, speaking of Emily, right? She just joined us. Okay, can you hear me, Emily?
Yeah, I can hear you.
Okay, so I want you to download your spreadsheet and open it in your computer. Okay, so I'm going to start
Okay.
the lab now. Isabella Cisnero, is she there? I don't see Isabella. Next is Gabriela Edwards. I don't see Gabriela. Arwa Paris. I don't see Arwa. Princess Gate.
Hello, I'm here.
Okay. Did you download your spreadsheet, Princess?
Yes, I did.
Okay. Thank you. Kimberly Morales. I don't see Kimberly. Next, Trin Hernandez. I don't see Trin. Stefan Kehayan. Stefan is here, right?
Yeah, I'm here. I'm here,
Oh,
and I have the lab 4 ready and downloaded.
okay. Thank you. Jeremy Landis. Hello, Jeremy. Jeremy is okay. Good. Thank you, Jeremy. Next is Paola Leones. Are you there, Paola? Looks like Paola is away from her computer. Star. Pedro Lopez. I don't see Pedro here. Isabel Medina. I don't see Isabel. Arian Navidius. I don't see Arian. Catherine Perez. I don't see Catherine. Next is Nadia Plum. Nadia is not here either. Jason Surveillon.
Yes.
Okay, thank you. Did you download your spreadsheet, Jason?
Yes, I've downloaded it.
Okay, thank you.
Mhm.
Dana Terry.
Yes, I'm here, and I downloaded it.
Okay, thank you. Ramon Moran. I don't see Ramon is here. Let's see who's that. Paula. Okay, Paula downloaded. Ramon is not here. Audrey Tylery.
I'm here.
Okay, you download the spreadsheet?
Yes.
Okay. And Carlo Gallardo.
I'm here.
Do you download the spreadsheet, Carlo?
Yes.
Okay, thank you. Is Steve Sanchez? Steve here. Yeah, Steve seems to be here. Okay. Especially the name. Okay, thank you. Next, Ben Bandoy. Ben seems to be here. Oh, yeah, replied. Okay, thank you, Ben. Noemi Martinez. Noemi Martinez. I don't see Noemi here. Next is Luis Cruz. Luis Cruz is here.
Yeah. I don't see the spreadsheet in my group folder.
Okay, which group? You're 16?
Yeah, 16.
Okay, let's see what's going on here. Thank you for letting me know.
Yeah, no problem.
Okay, I see it here. See that? L04, G16. Try to refresh your screen.
Oh. Can you name me the numbers again?
Hmm?
Is it L0 what? Sorry.
P07, L04. Lab 4.
Oh, okay. Okay, I got it. Yeah. Thank you.
This one highlighted here.
Yeah, I got it. Okay, appreciate it.
Okay, download it and open it.
Okay.
Next is Janie Maldonado. Is Janie there? I don't see Janie. Next, Mikara. I don't see Mikara. Next is Chris. I don't see Chris. Oh, wait a minute. Ryan. Is Ryan there? No. Chris. Okay. Delisha. I don't see Delisha either. Juan Torres Torellano. Torres Arellano. One. Okay, let's see how many students are here. Huh. Interesting. Oh, Max. Gosh, it's not Max that I want. Some. Okay, 14. So some students, 15. Some students didn't reply. Let's see. Was not called. Paola, you go. Paola reply. Now we have 15. Should be one more student. Was not called, by the way. Let's see. Juan Torres. Okay. That's just you. Okay, thank you, Juan. Did you download your spreadsheet, Juan? Okay, good. 16. Now all the numbers match. Okay. So you got an idea, right? How we put together the lab from this from this simulation. And we do have a voltmeter, right? In the simulation, we also have an ammeter. We're going to use both devices. We use both devices in this experiment. And there you go. 4. And how, let's go through my slides, right? So you know how we do that. That's another way of putting the circuit together. The first thing that you do is to measure the resistance, something with the multimeter, something that